equation? Okay. Well, we're gonna brush through some of this. Some of this is just gonna so that you get the concepts. Mark, you asked me what I'm doing when I go to Minneapolis. This is what I'm doing. I'm going to be teaching physical chemistry. This is this chapter. I've been going deeper into this chapter. So let's just look at it. All right, so here's the concept. And yesterday I had a little bit of problem here. It let me go along. It wouldn't let me write on here, and then it stopped advancing the slides. It's wanting me to put a password in. I'm having trouble doing this. So hopefully this will keep running. If it doesn't, I will switch over to this right here. So let me just warm this up. All right, so these are some of the things I want you to appreciate. So in thermodynamics, we get involved in energy, and we'll look at a reaction here in just a second that you're familiar with and bring in the energy. I want you to appreciate what an endothermic exothermic reaction is. Simply you'll see what these are. Enthalpy, entropy. There's some terms here. You've probably heard the term entropy. Everything tends towards disorder. Second law of thermodynamics has to do with entropy. This is the equation I want you to be able to work with. Kinetics deals with the rates of reactions. And then appreciate a little bit about what we mean by an equilibrium reaction. What do we mean by equilibrium? Equilibria. All right, so let's get into it. We're going to get into it right here. All right, here is I could write this reaction C8H18. This is octane. This is the main ingredient of gasoline. And your automobile brings in air, and the air is mixed. It has 20% oxygen in it. And it produces carbon dioxide and water. That is a chemical reaction. You know, we were introduced to this in Module 4. What is a chemical reaction? How to balance these chemical reactions. You have reactants, products. What we ignored is this. I mean, what we ignored was the main reason why you burn the gasoline. Right? You don't put gasoline in your car because you want carbon dioxide and water. If you want water, you go to the sink. And you don't want carbon dioxide because it doesn't support life. So here's a chemical reaction you know about. It produces carbon dioxide and water, but that's not what you want. That's what you want. Right? Energy. Oil prices went this past month, right? Everybody watching that? Well, you're watching it. Gasoline was $2.59, and now you can get gasoline for $2.05. Energy, and everybody said it all has to do with energy. Energy means all has to do with oil. Oil means what? It all has to do with gasoline that we're putting in our cars, that we're burning for this energy. Now this is an exothermic reaction. All right, just keep this in mind. Anytime you are burning anything, you're talking about an exothermic reaction. What is an exothermic reaction? It is a reaction that releases energy. All right? You burn a piece of paper. That's exothermic. You could tell it is exothermic because there's heat being given off. So there are reactions that require energy. The opposite of this one. Okay, Daniel, you want to become a billionaire? Okay, here's how to become a billionaire. convert carbon dioxide and water into gasoline. What is that? That's the reverse of that reaction. Okay? Do you think that would make you a billionaire? Just figure out how to turn carbon dioxide and water into gasoline? Well, you can do that. But the way you have to do that, it requires a lot of energy to do that. It's not saying that this reaction is impossible. It's not impossible. The oak trees outside are doing that all day long. They're converting carbon dioxide and water into, not the gasoline, they're converting it into sugar. They take carbon dioxide and water and they produce sugar and oxygen. And why doesn't that cost any money? Because they're taking the energy from the sun to do it. The sun's just shining on the trees, and the trees are capturing that energy from the sun. Lots of energy. More energy than we're burning in our cars. If you go through how much sugar is being produced by green plants on the earth and convert and go back and say how much energy does that take, you can do that. You can do these calculations in thermodynamics. This is thermodynamics. You can actually calculate this stuff. You can calculate the amount of energy, amount of calories, kilocalories, joules. And those are some of the terms for it. Okay, so this is an endothermic reaction. The reverse of that reaction is endothermic. It requires energy. Energy plus carbon dioxide plus water can produce gasoline and oxygen. That's endothermic. So whenever you're seeing energy as a reactant or on the left side of the equation, that's one way of seeing an endothermic reaction. It's required for the reaction to take place. We don't need any energy for this reaction to take place because it releases energy. It's exothermic. And if you took gasoline in a drum and burned it, you would get heat. It's about all you'd get. If you take it in an internal combustion engine, you get heat and work. So there is kind of a relationship between heat and work. You can take that energy and if you can capture it and convert it into work, it's not producing as much heat, it's actually doing the work. But here, okay, Joel, you want to become a billionaire. So here's your job. Daniel's going to work on this one, become a billionaire. You need to work on this one. The internal combustion engine only converts about 30% of that energy to work. 70% of it is because you got a radiator in the front of your car, getting rid of the heat that's being produced while you burn it. If you could get this down to 30 and that up to 70, your car could get 100 miles to the gallon. All right? If you doubled the amount of work you could get out of a gallon of gasoline.
Didn't you guys do that? Jeep? You use something, I forgot what.
Well, Southwest Research has a unit over there, a department over there that works on internal combustion engines. They're trying to design new engines. And
they put more combustion to the engine, which was less work for them, but it created less heat after.
Yeah. So there are. I had a student about 4 years ago, and his dad worked over there, and his dad actually worked on the engine concepts they're working on. The Wankel, there's a Wankel engine, doesn't use pistons. Okay. What?
They discontinued it because it's not reliable.
It obviously didn't take off real well. The Wankel, I remember hearing about that when I was in high school. I think they had the Wankel engine. Okay, so thermodynamics, the study of energy, work, and heat, applied to chemical change. Thermodynamics, a thermometer measures temperature. And so if the temperature in the room goes up, it went up because there was more heat pumped into this room. So the temperature is not equivalent to heat, but it is a way of monitoring or gauging that heat has come into the situation. In thermodynamics, and Mark, if it's better to see some of this with that light off, you decide. But in thermodynamics, they talk about a system and the surroundings. So if you want to study a chemical reaction, you have to kind of see where the boundaries are so you can see what's happening as a result of that chemical reaction and not just the surroundings. So if we're talking about an exothermic reaction, we've got a system here. It's releasing heat into the surroundings. It's going to make the temperature of the surroundings go up. If you have an endothermic reaction going on in your system, it's going to absorb heat from the surroundings and cause the temperature to go down. All right, so this is just talking about it right here. So this would be your exothermic situation. Here's your endothermic. It's pulling heat from the surroundings. And I think here's a couple practical examples. Cold packs. And if you, next time you're in Walmart, or not Walmart, Walmart, Walgreens, CVS, and you're buying a cold pack, or you have a cold pack, look on the back of it, and you'll see that's the ingredients. Ammonium nitrate. That's what's in the cold pack. And what's happening? So they have two containers in there. One has ammonium nitrate in it, the other one has water in it. Little plastic containers. The instructions say put it on a hard surface and press down on it and crush it. What are you doing? You're breaking a little seal between the water and the ammonium nitrate. Water flows into the ammonium nitrate. Those of you in 1105, you did the calorimetry experiment with ammonium nitrate, and the temperature goes down. What happens? The ammonium nitrate is absorbing energy from its surroundings. What's its surroundings at that point? Water. So the water's at room temperature, has a certain amount of heat associated with it at 20 degrees centigrade. You crush it, the water flows into the ammonium nitrate dissolves in the water, sucks the heat out of that water, and the water temperature goes down 4 or 5 degrees, and the pack gets cold. So that is an endothermic thing going on there. I don't call it a chemical reaction. That's ammonium nitrate going into solution. It's dissolving in the water. And pardon me for speaking fast, but I'm going to talk a little bit fast. So listen fast, okay? You don't have to turn up your volume. You have to turn up your speed. All right? So this is endothermic. It's absorbing that energy and making the temperature go down. Cold packs, you take iron and oxygen and probably maybe a catalyst in there somehow, because iron doesn't rust that fast, but you create a situation where that iron will actually react with oxygen fast. These things are in probably like in saran wrap or something that doesn't allow air to pass through the plastic. And then you open them up, you expose them to air. The iron starts rusting and producing iron oxide, and that is an exothermic reaction. It's giving off heat. Now down in Texas, I guess you use that if you got a backache or something like that, but up north, when you go skiing, you stuff those down in your boots, you stuff them in your gloves, your mittens, you go out there and they keep you warm. You go, that's nice, kind of hot. That's a hot pack. So this is exothermic, this is endothermic. You getting it? All right, Sodium hydroxide dissolving in water is exothermic. Not everything that dissolves in water it makes the water get colder. You put sodium hydroxide in water, you could get the water, and I've done it over here. I got the water up to an 80, 90 degrees centigrade by just trying to dissolve sodium hydroxide in water. Very exothermic. This is a chemical reaction. We'll get into this in chapter 11. An acid plus a base forming a salt and water. Well, you actually saw that reaction in the 1105 calorimetry. See, that's a good thing about sometimes 1105 being ahead of this, because you can kind of relate to that. Acid plus base forms a salt and water and produces a little bit of heat. This doesn't change it. You know, you can put salt and water. There's not a whole lot of heat involved there. So those are just some examples. All right, if we're talking about this gasoline, all right, where does this energy come from? Where does this, so this is kind of a general reaction. AB plus CD forms AD plus CB. Well, there are certain chemical bonds in here. This thing is made up of this molecule, and there's 8 of these carbons. 2, 4, 6, 8. These are all hydrogens coming off of it. So what do we have here? We have carbon-carbon bonds. We have carbon-hydrogen bonds. Here we have oxygen-oxygen bonds. And on this other side, we have carbon-oxygen bonds, and we have hydrogen-oxygen bonds. All right, just give you an example. We have certain kinds of chemical bonds in our reactants. We have new chemical bonds in the products being produced. There is a certain amount of energy associated with these chemical bonds. These are high energy bonds. High energy bonds. And they're going down to products that are lower energy and releasing the difference. Follow me? They're releasing. So what we have here is, you understand the concept of potential energy? You heard that? Let's see, what's the opposite of that? Kinetic energy and potential energy? Like a dam. A dam is the example they usually say. You have a river coming down, they build a dam. And they build this big, huge dam, and they back the water up there, and they say, that's potential energy. And you know it is, because you can run it through a generator. You run it through a generator, the generator spins, it produces electricity. You're converting that potential energy into kinetic, real energy, electrical energy. Well, this is chemical, the potential energy right here, okay? These bonds have associated with them some particular amount of energy. And these have a different amount of energy associated with them. And the difference is the energy they release. Follow me? So this is what's going on with chemicals. Let's look at a... So here's an example. We're using A and B, but let's say A is methane. See if I can make this a little bigger. Oh yeah, here we go, right here. So let's say A is methane with natural gas coming into your home right now. It's getting cold, and you turned on your furnace, and you're getting some oxygen out of the air, and it's burning the methane. What's the methane have in it? Just carbon-hydrogen bonds. And the oxygen, again, oxygen-oxygen bonds. And like I'm saying, relatively speaking, These are high energy bonds. This is why we're buying oil and trying to get oil out of the ground and things like that. There's energy packed in those molecules. But when they burn with oxygen, and you get down to here to have carbon dioxide and water, these are lower energy bonds. They're going down to actually more stable compounds. Methane is not a very stable compound. You know it isn't. If the room's full of methane, we have to leave because it's an unstable compound. It wants to go down to a more stable carbon dioxide and water. All right? And this is what we would call delta E, this difference in energy between our reactants and our products is the energy that will be released. It's the amount of energy that will be released. It's an exact amount of energy. You can calculate that. It's 211 kilocalories per mole of methane. Per mole of methane, you get 211 kilocalories of energy. Now you can see that it's referred to as E over here as energy, but we can talk about nuclear energy, we can talk about electrical energy, we can talk about mechanical energy, like an internal combustion engine, the work that your engine is doing, that's work. But H here is enthalpy. This is the term really associated with the heat energy associated with chemical reactions is enthalpy, okay? Enthalpy. So it is energy. It's a particular energy associated with chemical reactions. So don't get confused. There are times where this delta H and this delta E are going to be exactly the same, and there are times where they're going to be different. Like the mechanical, the engine, the car engine. I told you get 70% heat out of it and 30% work. You know, this would probably be where we distinguish the two. Here's the enthalpy, the heat of reaction we're getting out of it, and here's the mechanical work we're getting out of it. And that's going to really be the total energy. So don't get too bogged down in that. Just appreciate that when we talk about enthalpy, we are talking about energy associated with chemical reactions. Okay? And you see this little delta sign here. Yeah, I call it a little triangle right here, delta sign. Change in enthalpy. So delta refers to change in. Oh, I didn't spell change right. Change in. So delta H is the change in enthalpy. What does that mean? We don't always know. As a matter of fact, in most cases, we don't know what this is, what this number is right here. We got an energy scale right here, but we say, what is that number? Well, we don't exactly know what that number is. We don't exactly know what that number is. But we can know this difference exactly. Okay? So that's why we focus in on the change in enthalpy, not the fundamentally what that this enthalpy is or that enthalpy is. We talk about the difference in enthalpy. How much did it change? So there's burning methane, and here is just another example where you would have ammonia down here, and you're breaking ammonia back up into its two elements, nitrogen and hydrogen, And that is an endothermic process. So this is a stable compound. Those two are relatively unstable in relationship to the ammonia. All right, so I'm whisking through this. So that was enthalpy. That was fast.
Yeah.
Entropy. My kinetics this morning is fast. It's a fast reaction. Entropy. What is this all about? So you just saw, just keep in mind, H is the term or the letter we're using to associate with enthalpy. So now we're going over to a new letter, S. This is pretty basic, or this is pretty common protocol. When you see H, enthalpy. S, entropy. Entropy is another concept, and it does impact a lot of things, but particularly chemical reactions. Okay, it's a measure of the randomness of a chemical system. High entropy is highly disordered. Low entropy, well organized. Okay, I'm going to give you some examples of this. Let's look at this. Here's a system that has some order to it. Let's pretend here's two flasks. It's kind of hard to see, but there's a valve right here. Just kind of vaguely see that little valve right there. So let's say this is full of air, but over here we have a fragrance. We have a fragrance, and this side over here, no fragrance. So we would look at that from an entropy point of view, that there is some degree of order there. Over there, fragrance. Over here, no fragrance. And you open the valve. You open the valve, and spontaneously, the system moves to be more random. Okay? This is the driving. Entropy is just a kind of a natural drive for things to become more random. So you open the valve, you don't do anything, you just open the valve. What happens? Pretty soon, you got the same amount of fragrance in both sides of that container. Happens. What's the driving force? Entropy. Entropy is the driving force for that to happen. This system is spontaneously wanting to move to be more random, less organized. My office is this way. All right? Some students say, Mr. Rick, you're so organized. I go, oh man, it's in my office. Come to my office. I have to work at this. I have to work at folders. There's a 1305, 003, 006 folder, okay? And I have to work. Sometimes a student comes to me and says, Mr. Rick, I turned that paper. I say, okay, I have to look in my other files. And I do find it sometimes. Oh, there it is. Somehow I got in the wrong file. All right, so order doesn't happen spontaneously. Disorder does. You follow me? That's what the entropy is all about. So that's all it's saying down here. If I started here and with the valve closed, I just started here, and I opened the valve, this won't happen spontaneously. The fragrance won't just say, oh, let's all go into the left container. That's kind of the essence of entropy. So let's get a couple more examples here. So the second law of thermodynamics, the universe spontaneously tends toward increasing disorder or randomness. All right? So you have salt, sodium chloride crystals. So let's say this is sodium chloride crystals. Pretty ordered. I've shown you pictures of this before where there's a sodium ion and then around it, it's surrounded by chloride ions. The chloride ions are surrounded by sodium ions. So the positives are surrounded by negatives, the negatives are surrounded by positives. It's pretty ordered. It's in a crystal lattice. So that is, so if you go from a solid, well, probably the better example here is ice, because we're going to a liquid. I'm sorry. So let's use ice as an example. You got an ice cube, and the water molecules are actually in crystals, a crystalline lattice. And you just set it on the table, and it melts into a liquid. That thing has a definite volume and a definite shape. Here it only has a definite volume. It takes any shape. It can actually be a little bit more random. Okay, this has some randomness to it. It has a certain volume, but it can kind of take whatever shape it wants. An ice cube won't do that. Ice cube is very specific volume and shape. So that is going to, this is where entropy is increasing. It's going to more disordered state. And then if we take the liquid, if we take our liquid water and boil it, and the water molecules now are in the room. They're contributing to the humidity. What volume? Well, just tell me what the volume of the room is. And that water has now dispersed itself throughout the whole room. This entropy is increasing. It's becoming more random. And now here's the case where we would have, let's say we had sodium chloride and water. And we take a cube of sodium chloride and drop it into the water. The sodium chloride has got a certain amount of order to it. We've got a system here where here's salt, here's water, and now what happens? This dissolves into the water, and we have sodium and chloride ions uniformly dispersed. So in every one of these cases, every one of these processes, we are getting more random, higher entropy. Entropy, and another way to say that is that the change in entropy is positive. If we were to take the final entropy minus the initial entropy, the final entropy is a bigger number than the initial. Don't know what that number is, but it is going to be positive. Delta S is positive. Delta S is positive. So helium gas versus a solid, sodium solid, which one has higher entropy? Okay. Liquid water versus water vapor. Water vapor. All right. So we're not getting into any numbers. I just want you to kind of appreciate what is entropy, randomness. More random, the higher the entropy. And this I'm not going to even really go into. Just to introduce the fact that you can look at enthalpy and entropy associated with a reaction and decide whether the reaction will take place spontaneously or not. And maybe the best example is this ammonium nitrate. We've already seen that this plus water, it's going to go to ammonium ions plus nitrate ions. But it takes energy to do this. All right, so just wrap your mind around this. because this gets colder. You put that in the water, it gets colder. It takes energy to do this. So you can kind of scratch your head and say, if it takes energy, why would it do that? And it does it spontaneously. You put ammonium nitrate in water, and it spontaneously dissolves into the water, but it makes the water get colder. It's requiring enthalpy. It requires heat to do this. But what is happening here? It's becoming, the delta S is positive. It's becoming more random. All right? So ammonium nitrate dissolving in water is an entropy-driven process. Entropy is driving the process. It's becoming more random. You say, well, it costs energy. You have to invest energy, enthalpy, to make this happen. Why would it even happen? Well, it happens because entropy is driving this process, okay? So enthalpy and entropy have to be brought into consideration and understood to understand whether a chemical reaction will happen or not. Follow me? You can have one where it takes a lot of energy, but it's going to give a lot of entropy. It's going to give you back a lot of entropy, a lot more random. And so that gets you to Gibbs free energy equation. This is kind of the mother of all thermodynamic equations. Gibbs free energy. We could put Gibbs in front of this. And so G, delta G, is the change in Gibbs free energy. And you can see what are the things that have to be taken into consideration. What is the change in enthalpy for this particular process? What is going to be the change in entropy for this particular process? And at what temperature are you thinking about this reaction? Okay? What temperature are we at? And that's in Kelvin, absolute temperature. You don't need to do problems with this equation. I just want you to see the equation, and because I just, with the ammonium nitrate, I'm telling you, you have to know a little bit about this. It requires energy for ammonium nitrate to go into water, but it gives you back a lot of entropy, and then you need to know what temperatures is happening at. So ammonium nitrate dissolving in water might not happen at minus 80 degrees centigrade. Might not happen. You put it in there, doesn't dissolve, okay? Just because it dissolves at room temperature doesn't mean it's going to dissolve at another temperature. I was going to say one other thing right there. What was I going to say? Gives free energy. Oh, okay. Yeah, the example I was going to give is, let's take this sheet of paper. Whoa, 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 whoa. I didn't want the phone. Sheet of paper. Is this burning?
No.
Is this combustible?
Yes.
Will it burn?
Yes.
Okay. So, theoretically, not theoretically, really, you could take this piece of paper and put it in an oven. And you say, okay, at this temperature, this material does not spontaneously burn. Doesn't spontaneously burn. You know, I would need a match or something, and I could set this on fire and it would burn. But at room temperature, it's fine. But we say it is combustible material. You can wrap this up and start a fire in your fireplace, right? A bunch of this. You could take this and put it in an oven, turn the oven up. Let's say you had an oven that could go up to 1,000 degrees centigrade. So you turn the oven up and you just kind of watch it. You watch it. It gets up to 400 degrees. It's not burning. It's 500 degrees, 600 degrees. It goes up in flames. No match, nothing. Okay? you've reached a temperature at which this will spontaneously combust. You follow me? That's the auto-ignition temperature. Firemen would study that. They know auto-ignition temperatures. In other words, at this temperature, this table will burst into flames without any flame being near it. And so when firemen come to a house, what they start doing is busting windows and this and that. They're trying to get the heat out of the building. Because if the heat builds up in the building, it doesn't matter whether it's 5 rooms down. If stuff gets too hot, it's going to burst into flames automatically. It doesn't have to wait for the flames to get there, because the building is rising to the auto-ignition temperature of the combustible materials that are in the building. And firemen know that. What they need to do is, well, they're trying to smother it from air. They're trying to reduce the temperature. That's what they're trying to do to get this fire under control. They got to reduce the temperature, because other things will start, boom, bursting into flames automatically. And it's all related to this. There's certain things that will happen at a certain temperature that won't happen at room temperature. Okay. This is thermodynamics. So don't worry about this. You could, if you kind of knew the relationship between these two things, you could predict whether something is going to happen spontaneously or not going to happen spontaneously. An entropy. There's an example of entropy. Highly disordered, high entropy. You order those letters right in a sentence, low entropy. Takes work to do that. All right, so now, how do we measure some of these things? We can measure some of these things. How much energy can you get from a gallon of gasoline? You can measure that by burning a gallon of gasoline and seeing how much the temperature rises due to that. But you have to do it in a calorimeter. You have to do it and these are pretty simple. There's more complicated ones, but here's a simple one. And all you're doing, you got a styrofoam cup, and what is it doing? This is your system from the earlier slides. This is your system. This is your surroundings. Surroundings. Help me. Is that right? There's a U there. 2 R's?
Sure.
Sure. We'll believe you if you put 2 R's in there. Okay. Don't Google it. Don't Google it. Surroundings. All right, so that's all you're doing with the calorimeter is you're saying, okay, I want to study gasoline. I want to burn some gasoline. I want to figure out how much temperature comes out from that, or I want to dump ammonium nitrate in here and see how much the temperature goes down. But I don't want it to be losing energy to the surroundings or gaining energy from the surroundings. I want to isolate it from the surroundings. That's what the calorimeter is doing. Calorimeter, it's coming from the same word as calorie, which is a unit of energy. The calorie is a unit of energy. Calorimeter. And here is the calorimetry equation. Q here is just kind of, Q is just the amount of heat. And if it is a chemical reaction, Q can be related to the change in enthalpy. Not everything you would do in a calorimeter is a chemical reaction. You might take a chunk of aluminum, hot aluminum, and drop it into a little bit of water and say, okay, what happened? Yeah.
So when we were in lab and we used this equation, we had a negative M.
Right.
So is this different from
No, okay. The,
We have like the negative in SH.
yeah, Joel, we could have this. And what is the Q? The Q is the amount of heat that either got absorbed by the surroundings or released to the surroundings. And we could have the negative, which is the amount of heat absorbed by the system or released by the system. That's the only difference in that positive and negative term there. It's kind of like, what are you talking about? Are you talking about what's happening to the surroundings, or are you talking about what's happening in the reaction? So that's where that negative and positive term comes from. And we wanted to know the amount of energy being either absorbed or released by the chemicals we were putting in the calorimeter. Okay, so don't get confused by that negative and positive. It's kind of like, what's your reference point? What are you talking about? Are you talking about what happened to the surroundings, or are you talking about what happened in the calorimeter? All right, and we were talking about what's happening in the calorimeter. So let's see here. So yeah, why is this positive? Calculate the amount of heat needed to heat 27 grams of aluminum. Now this is a physical change here. All right, we're not even talking about a chemical reaction, but we are talking about something that requires heat. And what are we doing? We're taking aluminum, 27 grams of it, and we are heating it up. And we're heating it from 25 degrees C to 660 degrees C. Now I picked this temperature right here because that's the melting point of aluminum. So this is kind of how much heat does it take to melt aluminum, 27 grams of aluminum. All right, so the Q. So how much heat is it going to take from the surroundings, you know, whatever it is, a Bunsen burner or a hot plate or whatever it is you're using, how much heat is you're going to need to get from that to melt the aluminum? And so it's just simply the mass of the material you're heating. Well, let's use the way I've been doing it here, times the specific heat of the aluminum. Okay, now different materials have different specific heats. The specific heat of water is 1 calorie per gram degree centigrade. But aluminum, it's 0.215 calories per gram degree centigrade. And the delta T. Okay, delta T is always, where do I put that? Put it up here. Delta T is going to be the final temperature minus the initial temperature. And in this case, the final temperature is much bigger than the initial, so what is that? 635 degrees C. And notice here, the degrees C cross out, the grams cross out, and we're going to get an answer in calories. Calories, that's the energy term. What's the answer? 6,886?
3,686.
Okay, now we have 3 significant figures in everything. So give that to me in 3 significant figures. Anyone? 90. 3,690 calories. Okay? And then if I ask the question, okay, give that to me in kilocalories. Remember, where do you start? Start with what you're given, and then convert it. I got to put calories down here and kilocalories up here. And what's the relationship between calories and kilocalories? Kilo, 1,000. 1 kilocalorie is 1,000 calories, right? Calories cross out. You got 3.69 kilocalories. So it takes 3.69 kilocalories to... Now, in my 1311 class, we get into thermodynamics. We start with this problem, and it's just to show you what we're going, what I do with this. 27 grams of aluminum. 27 grams of aluminum. It's about 1 mole of aluminum. This is the amount of heat it takes to melt a mole of aluminum. And then what I do is I go back to our Alcoa example. Remember Alcoa? Remember that? Aluminum oxide plus carbon forms aluminum plus CO2. This is aluminum. And well, actually, it's energy plus aluminum oxide plus carbon forms aluminum and carbon dioxide. And we calculate that amount of energy. We calculate the delta H needed to make 1 mole of aluminum. 27 grams of aluminum. You follow me? And then we compare that. So what are we comparing? Does anybody have an aluminum can in here? Nobody came in here with a Coca-Cola. That's good. But you take an aluminum can, a bunch of aluminum, take 27 grams of aluminum cans and melt it and convert it into something else. All you got to do is melt it, and you convert it into this. Here, you have to dig this out of the ground, put it in a big truck, take it somewhere, do this reaction to it, and just this energy is about 40 times more energy than melting that mole of aluminum. Okay? So the best thing you can do for your environment is don't throw away an aluminum can. Get it into recycling. Because every aluminum can you get into recycling keeps that amount of aluminum being dug out of the earth and having to be converted into aluminum to make those aluminum cans. You follow me? It takes 40 times more energy, and this is what you can do with thermodynamics. You can say, okay, how much energy does it take to make aluminum? How much energy does it take to melt aluminum? Let's compare those two. Because you say, well, boy, you got to heat this can up and melt it and convert it into something. Yeah, but it doesn't take a lot of energy. 3.69 kilocalories, and this other one takes, I don't know, like, 40 times that. So 100 and some kilocalories to get you a mole of aluminum. Okay, now normally, is that Oh, okay. Here's the HCl. You need to go do this one after class. Use that equation. Let me give you a couple ideas here. You got this equation. In this case, you're dealing with water. There's your SH. Specific heat of that solution. You're dealing with water. You're going to get your delta T here, the final minus the initial, and your M is, you see, 1/10 of a mole of potassium hydroxide, 1/10 of a mole of HCl, but they weigh, all of those solutions weigh 150 grams. So, you know, you can calculate the heat involved, and then, you know, think about, is it endothermic or exothermic? And then it says, okay, what would be the energy evolved for each mole of HCl? So you're going to take that, the delta H you get, and you're going to have to divide it by 1/10 of a mole of HCl. And that will get you your delta H per mole. Okay, I got a couple more concepts to shoehorn in here this morning. Can we move on? You can do that later? Okay, do that later. And matter of fact, you got the answers. So don't look at the answers until you do that. Kinetics. We've got about 2 more things. Kinetics and equilibrium. Kinetics, just know that kinetics and thermodynamics are 2 separate arenas, 2 separate areas of concern. Thermodynamics looks at, will this reaction take place? Will it require energy or use energy? Will it happen spontaneously? That's thermodynamics. Kinetics is, how fast or slow is that reaction? Thermodynamics doesn't tell us how fast it'll happen. I mean, you can say this reaction is going to happen. It's going to happen spontaneously. But it won't tell you whether it's going to be an explosion or whether it's going to just kind of percolate along. An example, methane gas can explode. That's a fast reaction. The kinetics are fast. It starts releasing energy, and it gets to be a runaway reaction, and it explodes. Your car rusting is exothermic, gives off energy, but it's a slow reaction. Okay? You can do things to speed it up, but so rusting is slow kinetics and explosions are fast kinetics. So let's get to an example. Here's a situation where and someone studying kinetics has to say, I want to study this reaction. How can I follow the process? What can I measure to see that the reaction is proceeding and how fast it's proceeding? Here they're putting bromine in, does it say? They're putting bromine in like hexane. So this is bromine. Bromine is reddish orange. Hexane is clear, colorless. All right? It's colorless. So you put some bromine into hexane and it turns it reddish orange. And you watch it for a while and it starts getting lighter and lighter until finally the bromine reacts with the hexane and the color disappears. What's happening is the bromine, like this, that bond is colored reddish orange. But this bond is colorless. That's what's happening here. Is the bromine still there? Yeah, the bromine's still there, but it's not attached to a bromine. Follow me? And it loses the color. It loses the bromine color. Well, we have the calorimeter measures heat. We have colorimeters that measure the intensity of color. You can actually take a little vial of this, put it down into the colorimeter, and it'll tell you how much light is being absorbed at that wavelength. And then you can wait 15 minutes and put it back in there, and you go, oh, the amount of light being absorbed is decreasing. And so you could actually set up a graph. You could have a graph which is, this is time. Usually a kineticist always is measuring time. And this would be the color intensity off of this colorimeter. So it starts out here, and here, and here, and here. And so they are actually graphing the disappearance of the bromine with time. And this time would probably be in minutes. And you might be able to do this reaction in an hour and a half. In an hour and a half, you just kind of monitor it. In an hour and a half, colors disappeared. And you could get some kinetic data on the rate of the reaction. And it would be so many moles of bromine per minute is reacting. At that temperature, at those concentrations, you'd get some data. This is what a kineticist is doing. Yeah, so other reactions, let's see, what's another example? Iron rusting. Lavoisier was a French chemist back in probably late 1700s. And he got kind of fascinated with rust. And he took a steel wire and he put it in a tube and he blew warm air over it. He weighed the wire. He put it in the tube, blew warm air over it for a day or two, took the wire out and weighed it, and he says, it's getting heavier. The wire is getting heavier. You know, that wasn't immediately obvious. There's rust forming on it. Is it getting heavier, lighter? What's it doing? Lavoisier said, it's getting heavier. So he did, it's getting heavier, heavier. So he's studying the kinetics of that. But he also said, he said there's something in the air that's reacting with the iron and making it get heavier. So there was a little experiment that he was doing. And so, you have to, you're trying to study a certain reaction, you have to say, how can I study this? What can I measure? What is happening that could actually give me a little window into what is going on there? Okay, so that's about all I want to say with kinetics. Two more things. Rate. What affects kinetics? What affects rates of reaction? There is a activation energy. So we looked at methane going down to here before, but what we ignored is there is a hump you have to get over. To get here on a Monday morning, there's a hump you have to get over, right? You got to wake up early and rub your eyes, take a shower, brush your teeth, and that's the activation energy. You do all of that before you get here. You get here and everybody thinks, boy, you look so nice and sharp and crisp and clean and wide awake and full of energy. But you say, well, you should have seen what I had to do to get here. All right, that's the activation energy. Had to get on 1604 and all that. So there's a certain hump you have to get over to even get to that reaction, even though you're going to produce energy from the reaction, activation energy. And what do I want you to understand there is that catalysts lower activation energies and therefore speed up reactions. So that's one way of speeding up a reaction. Even if the reaction is endothermic, there is still a big hump you get to get over, and then you come down to the final energy of the products. There is still, that is your activation energy right there. The difference between that additional energy that's needed to get this reaction going. All right, concentration of reactants affects kinetics. All right, and the temperature of the reactants. So as the temperature increases, rate increases. Concentration increases, rate increases. Now let me try to help you understand that at a molecular level. For a reaction to take place, let's say you have nitrogen and hydrogen, and you're going to form ammonia. So you have nitrogen plus hydrogen, and you're going to form ammonia molecules. Well, let's leave these out of here for a second. Let's just think of this. These are two separate gases, nitrogen and hydrogen. For them to come together and become an ammonia molecule, what do they have to do? They have to meet. All right? They have to get to be in the same place. They have to collide to form that ammonia molecule. That's one thing that has to happen. So, if you increase the concentration of these things, raise the pressure so that you have more nitrogen and more hydrogen there at the same time, what's happening? Nitrogen and hydrogen molecules are colliding with each other more frequently. You follow me? This is what concentration is doing to the rate of a reaction. It's increasing the collisions so that this can happen. What is temperature doing? Now get in my mind now and think about this. What does temperature do to those molecules?
Increase the energy.
It increases the energy. What does that do to those molecules? They move faster. So now they're slamming into each other harder. Okay? So you could have, at a certain temperature, you could have ammonia, or you could have nitrogen and hydrogen bumping into each other and nothing's happening. Nothing, they don't react. So just bumping into each other doesn't mean they react. They have to bump into each other enough that bonds break and new bonds form. And you raise the temperature and bam, they're slamming into each other. On the homework, I think I have this 1604 example. Concentration. You have a lot of traffic on the road, you have more accidents. You raise it, what would happen on 1604 if all of a sudden Texas decided 90 miles an hour is fine?
That'd be awesome.
That'd be awesome.
That'd be awesome. What about accidents? Increase. What about the intensity of those reactions? Increase. All right? The damage that would be done and all that sort of thing would go up. Why? Because everything's moving faster. Okay, now equilibria you're going to have to learn on your own. Not all reactions are equilibria reactions. Gasoline burning is not an equilibrium reaction. It produces carbon dioxide and water. But if you put a vinegar in water, you get an equilibrium between the vinegar molecules and the acid they form. All right? If gasoline was an equilibrium reaction, we could go back and forth between gasoline and carbon dioxide and water. It'd be a happy little equilibrium. But it isn't. It's a forward reaction. So not all reactions are equilibrium reactions. All right. This is due Thursday morning. Okay, one last thing before you leave. When you come on Thursday, you have to have Now, I don't say have to. I'm going to let you in if you don't have this. But you come with the calculator you're taking into your exams. We're going to start learning the log key and the 10 to the x key. They work differently on other calculators. You bring the calculator, and if you don't have one, you go buy one. The calculator, you're going to bring the exam 3 and the final exam. You do not want to learn how to use these keys with the exam sitting in front of you. Follow me? All right, so everybody bring their calculator on Thursday.
Mr. Rio, can I get the paper homework?
Yeah, is there anybody that didn't get the homework?
I did.
I have homework. Oh, here you go. Yeah, that's Tuesday. That's Thanksgiving. Do we have any more? Joel, what did we do a week ago last Tuesday? We finished solutions. Is that
I
what
think
it
so.
Yeah, we did weight, volume, percent, osmotic pressure, ligative properties.
The liveliest person in the class besides
I will try to, I'll go back to my office now and I'll try to get a,
Yeah, we did the water.
yeah, I'll try to get a lecture up. Okay.
I really don't get how we have a final in the class.
I walked in late, so I didn't know if you handed out any homework or
No, you got this one?
from last week.
Yeah.
Yes, I have it.
And this is due Thursday?
Thursday,
Yeah,
okay.
that's
Quick
it.
question.
There was something to pick up. Did everybody pick up their papers?
Not everybody.
Okay.
Do we need a lab coat and goggles?
No.
Okay.
No, we're just going to review for the final. 11 o'clock.
You had sent out an email about the grade.
Oh, so we can bring it.
I don't know, you said something about the grade.
I sent an email to you personally.
Everyone. There's an inbox.
Yeah. Can you pull it up? Pull it up and I can explain it to you. But I'm trying to remember it offhand.